Hello everyone, my name is Court, and this is going to be your exam review for your first exam of spring 2023 for your Calculus 1 class. First exam, hooray! What's this fall 2022 doing up here? Well, this was the old exam. This was the exam one from last semester, so we're going to be working through this one to better equip you for your exam coming up. Please note that you should not just watch this video. You should study some other things, like perhaps your homework problems, because that's a good way to study for your exam. Then you'll get a good score. You'll be very pleased with yourself. Anyway. Okay, so on to the question. So, question 1, part 1. Suppose a function y is f of x has a jump discontinuity at x equals a. Which of the following statements must be true if the function f is continuous at all other input values? I think this one's supposed to say if. Okay. Well, let's just go one by one with our answers. Do a process of elimination. So, the first one says, limit of x approaches a from the left side equals f of a, and limit of x approaches a from the right side equals f of a. It says there's a jump discontinuity, so this isn't entirely true because I'm just going to make a little graph with a jump discontinuity here. See, this has a jump discontinuity, but here's limit from the left side and here's limit from the right side. They're not the same, right? So obviously this is not entirely true. So we're not going to circle A. How about B? B says, suppose x approaches a from the left side, that limit equals f of a, or x approaches a from the right side equals f of a. Well, can we come up with an example to disprove this one also? I can. What if we make another hole right here? Right? Well, then neither of them are going to equal f of a. Or, better yet, what if we did this? Put a little dot here. And then maybe something like this. This isn't true either, right? Because f of a, the limits approach at those spots, but f of a is right here. So it can't be those. Oh, let's go on to answer C. Limit as x approaches a from the left side is plus or minus infinity, or from the right side is plus or minus infinity. Well, this graph we already sketched disproves that neither of them are. This is a jump discontinuity, and neither of them are infinity. So this is limit as x approaches a from the left side, and limit as x approaches a from the right side exist and are not equal. Well, that would actually match up here, right? In fact, I think that's your answer. Let's go over E just to be careful, though. I guess maybe to explain D. This limit exists. It's right here. This limit exists, but they're not the same, right? Because it's a jump. So E, limit as x approaches a from the left side is limit as x approaches a from the right side, and they're both equal to f of a. Well, this drawing we made also disproves that one, right? So there we go. I think your answer is D. Okay, part 2. Equation of the line tangent to the graph f of x at f of x the square root of x at x equals 2 is which of the following? Well, we gotta just find out the equation of the tangent line. So to do that, we have to find our derivative of our function, right? Remember, you can write square root of x this way. That'll let you use the power rule, right? Then derivative x to the 1/2 would equal 1/2 x and a negative 1/2, right? We can rewrite that as 2 square root of x, right? Because the negative power is just going to bring it to the denominator. So anyway, this has to be our slope, right? Because that's what our derivative is. So now tangent at x equals 2. Well, this means that the tangent line has to share a point on the graph, right? They have to be at the same spot. So let's see what's the point on this graph. On this graph here, we have the following point. We've got 2 for x, right? Then we get square root of 2. So we want our equation for our line to have the same point on there. Well, we can use point slope form. I'm going to write it over here to the left in green. So remember, y minus y1 equals mx minus x1, right? Where m is the slope and x1, y1 is a point. So we can do the same thing here. So we'll have y minus square root of 2, right, equals 1 over 2 square root of x minus 2. That there would be the equation for a line. So if we just add 2 over, y equals 1 over 2 square root of x minus 2 plus square root of 2. And let's see if any of these answers is that. I'm just looking through the answers. I think it's E. Well, there we go, because it's 1 over 2 square root of x minus 2 plus 2, plus square root of 2, sorry. So there we go. All right, so part 3. If limit as x approaches a of f of x equals L, where L is a real number, which of the following must be true? 1 says f of a equals L. 2 is limit as x approaches a from the left side is L. And 3 is limit as approaches a from the right side is L. So what do we think? Well, let's go about the first one. If f of a would equal L, I'm just going to come up with an example here. Let's just say that's a little hole right there, by the way. Right? Say this is L, but the function value maybe is up here. Well, this would be true then. Limit as x approaches a of f of x equals L, right? But f of x would not equal L, right? F of x would equal this value up here. So this means that this is a way to disprove one. So that's not always true. What about the other two? Well, remember the definition of an overall limit, right? For left and right hand side, like this one here. That means that the limit from the left and the right hand side both have to be approaching the same spot, right? So this means that this is true, because for there to be an overall limit here, the limit from the left and right hand side have to be going to the same place. So they both have to be equal to L. So we'll say 2 and 3. 2 and 3 is correct. All right, so now we're at part 4. So graph of the function is shown below. What is the average rate of change on f of x with respect to x over the interval 0 to 5? Well, we start here at 0, right? Then we go over to 5. Let's get a different color here, maybe. Yes. Start here at 0, move over to 5, right? Well, what's the y value here? 3. Y value here, one's 1. So as x changes 5 spots, a change of positive 5, right? How does y change? Well, y changes by going down 2. Well, then we know average rate of change, right? Delta y over delta x. That would equal negative 2 over 5. Hey, looky there. That's option A. So let's circle that one. Okay, so for part 5 here, suppose f prime of a is less than all this for delta x is greater than 0. Which of the following could be the graph of f? Then we have 4 options. So this seems intimidating. I can't blame you, but what's this here? Well, this is the instantaneous rate of change, right? What's this? Well, that's the average rate of change. average rate of change between basically the point A and some further point. So we just want to know which graphs have the instantaneous rate of change at A is less than this other one, right? Let's start with this one. The point A. I'm just going to draw a little tangent line to represent instantaneous rate of change here. Now let's draw a secant line, which is just going to represent that other part, that average rate of change. For some delta x is greater than 0, I'm just picking a delta x that's out there, right? Well, you'll notice the blue one has a smaller slope, right? The blue one being the average rate of change here. Maybe I should. Blue one being the average rate of change. So that this doesn't follow our criteria, because we want the instantaneous to have a smaller slope. Okay, so let's look at this one. All right. Okay. Now which one has a bigger slope? Well, that would be the blue one, the average rate of change. So let's say 2. 2 is a graph that satisfies this property. Well, let's keep going down the line. Very methodically draw my tangent line here. Well, now let's make the same thing. Let's make a secant line. Notice all this is f prime of A. So this is what's the tangent line at A? Okay. Well, which one has the larger slope? That's the blue one. So 2 and 3 so far satisfy this property. Check our last one. All right. Okay. Notice the green one has the higher slope now. So, yeah, I'd say pick D. 2 and 3 only would be my professional opinion.
So for problem 2, it says considering the following function, and it's a piecewise function. It says f is equal to 2x squared minus 7x minus 6 when x is less than 1, and when x is greater than 1, it's going to be negative 5 minus 8x. So the first problem says compute the limit from as x approaches 1 from the left side, from the negative side of f. So if we kind of draw this graph, it's going to be broken up at 1, so we have 1 here, and this part will kind of look like this, kind of quadratic, and then it will have a linear side here. And we're going to compute the limit from the left side here. So that means it's going to be from the quadratic side. So I would take my limit as x approaches 1 from the left side of f, which is going to be this quadratic equation. And then I'm just going to plug in 1, and we get the limit x approaches 1 times 1, 6, and I'm going to get, we have 2 minus 7 minus 6, which is equal to negative 11. So that is the limit from the left side. And now we're going to do the same thing from the right side. The right side is the linear side. So we're going to see how that approaches 1. So we have the limit, x approaches 1 from the right side, negative 5 minus x, and then we're just going to plug in 1 because there's no boundary restrictions. 1, we're going to get that equals 5 minus negative 13. So, the next question says, does the limit as x goes to 1 of f exist? So the thing about this is that if the limit as x approaches negative 1, or if is equal to the limit of f as x approaches 1 from the right side, if those are equal, then the limit exists as it approaches 1 from both sides. Exists. However, this is not true. Limit of x approaches f is not equal. So limit approaches the left of f because it's negative. It's not equal to 13. So the limit of f does not exist. Is f continuous at 1? No, because the limit does not exist. If it was continuous, then the graph would be connected. It would look like this. Oops. Erase that. The graph would look like this. It would kind of curve and then stop here at 1, and then this linear part would take over here, and it would be continuous right there. But however, this function actually looks like this, and then this part's down here, and see they do not connect here. So no, because the limit as x approaches 1 of f does not exist. All right. For problem number 3, it says, answer the following questions based on the graph f below. Assume that all critical points, all points of discontinuity, and end behavior of f can be observed from the graph below. Asymptotes are indicated by dotted lines. It says, give numerical values for each of the following, right? Does not exist if the value does not exist. So, first part says the limit as x approaches 2 of f of x. So, I'm going to look at my graph here. And so I'm going to look at my graph. I see 2's here and go up. There's a hole here. So I'm going to see where it approaches from the left and the right. And as I go to 2, it looks like here on this side it's approaching 2. And on this side it is also approaching 2. So I can say that since it's the limit from the left side and the right side are the same, I'm going to say that the limit as x approaches 2 is equal to 2. Now, it's saying f prime of negative 8. Now, f prime means I'm trying to find the rate of change at point 8 or the slope of the line. So I'm going to go to point 8 and I'm going to come up and it's right here. And this point of the graph, it looks like a critical point. It looks like a minimum. And we know that at all critical points, the slope is equal to 0. This line here is flat. So I'm going to say the slope where f prime of negative 8 is equal to 0. All right, the limit as x approaches negative 2 from the negative side. So I'm going to go to negative 2 right here. We have an asymptote here. So from the left side, so I'm going to go to the left here. It's the left side of the graph. I'm going to go down and here. There's a point right here, a solid point. So I'm going to say as the limit approaches -2 from the left side, it goes all the way down to -3, all the way to that solid point. So f of -2 as it approaches from the left side is equal to -3. The limit as delta x approaches 0 of 3 plus delta x minus f of 3 of delta x. So I know that this is the limit definition of the rate of change of a point, and I'm seeing that x here is equal to 3. So we have x plus delta x in this case, so that's saying that we're going to try to find the rate of change of 3 as that delta x goes to 0, which means we're looking for the instantaneous slope when x is equal to 3. So I'm going to go to my point 3, it's about right here, and I'm going to go up here, and I can see that this section is a linear line. So that means I can just use the slope of a line equation to find out what it is, and I can use this point 2, 2 here, and go up to 3, 3, and so I can say 3 minus 2, or here I'll write delta y over delta x is equal to 3 minus 2 over 3. It's equal to 1 over 1, so the slope here is equal to 1. Right, and I can also do that visually on the graph. Here we have 3, and here we have another point that is delta x away. Whenever this point gets closer and closer, the line between them is going to stay on this linear line here. So that means that whatever the slope of this little section here is going to be the slope at 3. So, all right, next part. The limit as x approaches -6. So I am going to go to -6. It is right here. So -6 is right here at the peak. I can go from the left side, it goes all the way up to 5. And go to the right side, it goes up to 5. So I can confidently say that this is equal to 5. So the difference in y over the difference in x at -4, right? So this is just a fancy way of saying f prime, df, that's the change in f, which is also equal to the change in y, over the change in x, delta f over delta x, at -4. So I'm going to go to -4 here, and we have another linear line here. So I know that the slope of this linear line is going to be the slope at -4. So I can just take this point here at 6 and this line at 4, and I can do my delta t here. So we have -4, 1, and -6, 5. So delta y over delta x, 2, 5 minus 1 over minus 4. So this is going to be equal to 4, and that's going to be equal to -2. So my slope here is going to be -2. So moving on, the limit as x approaches 2 from the left of f of x minus f of -6 minus x minus -6. So if I notice I have two f's here, so these are going to be my y. So y minus a y value over my x minus an x value. So x2, x2. So it's looking for the average rate of change at 2 from the right side, from the positive side. So I'm going to go to my graph, and I'm going to go look at -6. -6 is right here. We found that in a previous problem. And then we're going to go to 2, or yes, 2 from the right side, and that's going to be here at 2. So as the limit approaches 2, this is going to be f of 2 minus f of -6 over 2 minus -6. And so f of 2 is equal to 2 minus f of -6, which is 5, all over 2 plus 6. And so this is going to be equal to -3 over 8, which cannot be simplified anymore. The limit as x approaches 0. So I'm going to go to my graph here, and I can see that 0 is right here. This is x is equal to 0 right here, and that's equal to 3. And so I'm going to go from the left side here, and that approaches 3, and I'm going to come from the right side, and that also approaches 3. So I can confidently say that the limit as x approaches 0 of f is equal to 3. Now the last one, the limit as x approaches 4 of f of x. So I'm going to come up here, and I'm going to grab my laser pointer, and I'm going to see from the left side, here's 4 right here. From the left side, 4 approaches 4. And then from the right side, 4 approaches 5. So we have 1, where from the right, the limit from the right, as x approaches 4 from the right, is equal to 4. And the limit as x approaches 4 from the left, or from the right, that is equal to 5. And since 4 is not equal to 5, then this limit does not exist. Because for the limit to go to 4, it has to be equal from both sides, and it's not. So this limit does not exist. And then part B, identify a value of f in the interval 10 to 10, which is continuous but not differentiable. So I'm going to come up and look at my graph and see where that is possible. So in places where, this is in places where the graph kind of breaks and has points that are not continuous. So places like, looking at the graph here, right? This slope, this point right here is not, it might be continuous here, but we can't tell what the slope is, because from the left side here, we have this quadratic here, and from the right side, we have this linear line. But here, it's just a point, and a point, like a mountain peak kind of tip, that doesn't have a slope. It's kind of ambiguous what it is, and so for that reason, there is no defined slope there. There can be a slope that we can find from the left side and the right side, but those are going to be different numbers, and for that reason, an example of x equals -6 is continuous, because there's no breaks, there's no jump, there's no discontinuity, but the slopes on each side are not the same. So for that reason, we can come back down here and write that x equals -6 is an example of where f is continuous but not differentiable.